Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Greetings everyone. I'm interested in learning more about a recent study that explores the application of transformer neural networks to model predictive control. Could you provide some background information on this topic?
Certainly. Model Predictive Control, or MPC, is a control technique widely used in various industries to optimize the performance of complex systems. It involves predicting future behavior, simulating possible actions, and selecting the optimal control action to achieve desired outcomes. Transformers, on the other hand, are a type of neural network architecture that has gained popularity in natural language processing tasks. They excel in capturing long-term dependencies and relationships within sequential data. The combination of MPC and transformers offers several advantages. By leveraging the strengths of transformers in time series forecasting, we can enhance the predictive capabilities of MPC, leading to more accurate and efficient control.
Thank you for the informative background. The report mentions 3 key contributions. Could you elaborate on each of these contributions and their significance in the context of MPC? 1. A new MPC system based on a transformer time series architecture. 2. A training method enabling multistep-ahead prediction for time series machine learning models. 3. Validation of the enhanced time performance of multistep-ahead transformer MPC compared to one-step-ahead SDM networks. Can you explain how these contributions address the challenges and limitations of existing MPC approaches?
Transformer is a type of neural network that is particularly well suited for processing sequential data. It is able to learn the relationships between different parts of a sequence and to make predictions based on these relationships. This makes it ideal for use in Model Predictive Control, MPC, which is a technique for controlling a system by predicting its future behavior and then taking actions to optimize its performance. MPC is a control technique that uses a model of the system to predict its future behavior. This model is then used to calculate the optimal control actions that will achieve the desired system performance. However, traditional MPC methods can be computationally expensive, especially for complex systems. This is because they require the model to be solved at each time step, which can be a time-consuming process. Transformer can help to reduce the computational cost of MPC by learning the relationships between different parts of the system's behavior. This allows it to make predictions that are more accurate than traditional MPC methods, even when the model is not perfect. As a result, Transformer can be used to control complex systems more efficiently and effectively. Here are some specific examples of how Transformer is helping to improve MPC. Reduced computational cost. Transformer can reduce the computational cost of MPC by learning the relationships between different parts of the system's behavior. This allows it to make predictions that are more accurate than traditional MPC methods, even when the model is not perfect. As a result, Transformer can be used to control complex systems more efficiently and effectively. Improved prediction accuracy. Transformer can improve the prediction accuracy of MPC by learning the relationships between different parts of the system's behavior. This allows it to make predictions that are more accurate than traditional MPC methods, even when the model is not perfect. As a result, Transformer can be used to control complex systems more precisely and accurately. Increased robustness. Transformer can increase the robustness of MPC by learning the relationships between different parts of the system's behavior. This allows it to make predictions that are more accurate even when the system is subject to disturbances or uncertainties. As a result, Transformer can be used to control complex systems more reliably and robustly. Overall, Transformer is a powerful tool that can help to improve the performance of MPC. It can reduce computational cost, improve prediction accuracy, and increase robustness. As a result, Transformer is a promising technology for use in a wide range of MPC applications.
Thank you for the detailed explanation. It is clear that Transformer offers significant advantages for MPC in terms of computational efficiency, prediction accuracy, and robustness. I am curious to know how the proposed MPC system based on Transformer time series architecture is implemented. Specifically, how is the Transformer model trained to make multistep-ahead predictions, which is crucial for effective MPC? Can you provide some insights into the training process and the techniques used to ensure accurate and reliable predictions?
Sure. I can explain how the transformer model is trained for multi-step-ahead prediction and is essential for effective MPC. The transformer model is trained on a dataset of historical data that includes both input and output variables. The input variables are the manipulated variables, MVs, that are used to control the process, and the output variables are the controlled variables, CVS, that are measured by the process. The transformer model is trained using a supervised learning algorithm. This means that the model is given the input and output data, and it learns to map the input data to the output data. The model is trained by minimizing the error between the predicted output and the actual output. Once the transformer model is trained, it can be used to make predictions about the future values of the CVS. This information can then be used by the MPC controller to calculate the optimal values of the MVS. The transformer model is essential for effective MPC because it can make accurate and reliable predictions about the future values of the CVS. This information allows the MPC controller to calculate the optimal values of the MVs, which can help to improve the performance of the process. Here is a summary of the training process for the transformer model. 1. Collect a dataset of historical data that includes both input and output variables. 2. Preprocess the data to remove any noise or outliers. 3. Split the data into a training set and a test set. 4. Train the transformer model on the training set. 5. Evaluate the performance of the transformer model on the test set. 6. If the performance of the transformer model is not satisfactory, then adjust the hyperparameters of the model and retrain the model. Here are some of the techniques that are used to ensure that the transformer model makes accurate and reliable predictions. Use a large dataset. The more data that the transformer model is trained on, the more accurate its predictions will be. Use a deep transformer model. A deep transformer model has more layers than a shallow transformer model, and this allows it to learn more complex relationships between the input and output variables. Use a regularization technique. Regularization techniques help to prevent the transformer model from overfitting to the training data. Use a cross-validation technique. Cross-validation techniques help to ensure that the transformer model is making accurate predictions on unseen data.
Thank you for the detailed explanation of the training process and techniques used to ensure accurate predictions in the transformer model. It is evident that careful consideration has been given to maximizing the model's performance and reliability. In practical MPC applications, it is common to encounter constraints on the manipulated variables, MVs, and controlled variables, CVS. How does the proposed MPC system handle constraints? And what techniques are employed to ensure that the calculated optimal values of MVs satisfy these constraints while optimizing the system's performance?
In practical MPC applications, it is common to have constraints on the manipulated variables, MVs, and controlled variables, CVS. How does the proposed MPC system handle constraints, and what techniques are employed to ensure that the calculated optimal values of the MVS satisfy these constraints while optimizing the performance of the system? The proposed MPC system handles constraints by incorporating them into the optimization problem that is solved at each time step. The constraints can be linear or nonlinear, and they can be applied to the MVs, the CVS, or both. To ensure that the calculated optimal values of the MVs satisfy the constraints, the MPC system uses a technique called constraint handling. Constraint handling is a method for modifying the optimization problem so that the constraints are taken into account when calculating the optimal solution. There are several different constraint handling techniques, and the choice of technique depends on the specific constraints and the optimization algorithm that is being used. One common constraint handling technique is called penalty methods. Penalty methods add a penalty term to the objective function that is being minimized. The penalty term is a function of the constraint violations, and it is designed to discourage the optimization algorithm from violating the constraints. Another common constraint handling technique is called barrier methods. Barrier methods add a barrier term to the objective function that is being minimized. The barrier term is a function of the distance between the current solution and the constraints, and it is designed to prevent the optimization algorithm from getting too close to the constraints. The proposed MPC system uses a combination of penalty methods and barrier methods to handle constraints. This combination of techniques provides a robust and efficient way to ensure that the calculated optimal values of the MVS satisfy the constraints.
Thank you for the explanation of constraint handling in the proposed MPC system. It is clear that careful consideration has been given to ensuring that the calculated optimal values of the manipulated variables, MVs, satisfy the specified constraints while optimizing the system's performance. In addition to handling constraints, another important aspect of MEPC is the ability to handle disturbances. Disturbances are unexpected changes in the system that can affect its performance. How does the proposed MPC system handle disturbances? And what techniques are employed to mitigate their impact on the system's performance?
The proposed MPC system addresses disturbances by leveraging the predictive capabilities of the transformer model. When disturbances occur, the transformer model can predict their impact on the system's future behavior. This allows the MPC controller to adjust the control actions proactively, mitigating the effects of disturbances and maintaining the system's stability and performance. To further enhance the system's resilience to disturbances, several techniques are employed. 1. Robust optimization. The MPC controller incorporates robust optimization techniques to account for uncertainties and disturbances in the system. By considering worst-case scenarios, the controller can make decisions that are less sensitive to unexpected changes. 2. Adaptive control. The MPC system employs adaptive control algorithms to adjust its parameters and control actions in real time. This allows the controller to adapt to changing operating conditions and disturbances, ensuring optimal performance over a wide range of scenarios. 3. Error feedback. The MPC controller uses error feedback mechanisms to correct for any deviations from the desired system behavior. By monitoring the system's response and adjusting the control actions accordingly, the controller can minimize the impact of disturbances and maintain the desired performance. 4. Constraint handling. The MPC controller incorporates constraint handling techniques to ensure that the control actions comply with system constraints and safety limits. This prevents the system from operating in unsafe or undesirable regions, even in the presence of disturbances. By combining the predictive capabilities of the transformer model with these disturbance mitigation techniques, the proposed MPC system can effectively address disturbances and maintain the system's performance and stability.
Thank you for the detailed explanation of how the proposed MPC system handles disturbances. It is clear that the system takes a comprehensive approach to mitigating the impact of disturbances on the system's performance. One aspect of MPC that is important for practical applications is its computational efficiency. In real-world scenarios, MPC controllers need to make decisions quickly enough to keep up with the dynamics of the system being controlled. How does the proposed MPC system address computational efficiency? And what techniques are employed to reduce the computational burden while maintaining the system's performance?
The proposed MPC system addresses computational efficiency by utilizing a transformer model with multi-step prediction capabilities. Unlike traditional LSTM models that perform sequential computations for each time step, the transformer model can process the entire prediction horizon in parallel. This significantly reduces the number of sequential computations required for MPC optimization, making it more computationally efficient.
Thank you for the explanation of how the proposed MPC system addresses computational efficiency. The use of a transformer model with multi-step prediction capabilities is a significant improvement over traditional LSTM models in terms of computational efficiency. Another aspect of MPC that is important for practical applications is its ability to handle nonlinearities in the system being controlled. In real-world systems, nonlinearities are often encountered, and it is important for the MPC controller to be able to handle these nonlinearities effectively. How does the proposed MPC system address nonlinearities? And what techniques are employed to ensure good performance in the presence of nonlinearities?
The proposed MPC system handles nonlinearities by employing various techniques such as adaptive tuning. The MPC controller continuously adjusts its parameters based on real-time data to account for changing process dynamics and nonlinearities. This allows the controller to adapt to varying operating conditions and maintain optimal performance. Nonlinear Model Predictive Control, NMPC. NMPC algorithms explicitly consider nonlinear process models in their optimization formulation. This approach enables the controller to capture complex system behaviors and nonlinearities, resulting in improved control accuracy and stability. Neural network-based MPC. Neural networks can be incorporated into MPC to approximate nonlinear process dynamics. By training the neural network on historical data, the controller can learn the complex relationships between inputs and outputs, enabling it to handle nonlinearities effectively. Hybrid MPC. Hybrid MPC combines linear and nonlinear models to represent different aspects of the process dynamics. This approach leverages the strengths of both linear and nonlinear models to achieve improved performance in handling nonlinearities.
Ladies and gentlemen, esteemed guests, as we conclude this insightful discourse, I extend my heartfelt gratitude for your active participation and thought-provoking questions. Today, we have delved into the transformative power of transformer neural networks in Model Predictive Control. We have explored how the transformer architecture empowers multi-step-ahead prediction, unlocking new possibilities for predictive capabilities. We have emphasized the importance of training with large datasets, deep models, and employing regularization and cross-validation techniques to ensure accurate and reliable predictions. The incorporation of constraints and disturbance mitigation through penalty and barrier methods, robust optimization, adaptive control, and error feedback provides robustness and stability to the MPC system. To address computational efficiency, we have highlighted the use of parallel processing for multi-step predictions, significantly reducing the computational burden. Additionally, the system's ability to handle nonlinearities through adaptive tuning and hybrid MPC techniques demonstrates its versatility and applicability in complex real-world systems. As we move forward, let us continue to explore the remarkable potential of transformer neural networks and their transformative impact on model predictive control. Thank you once again for your unwavering attention and engagement. Have a wonderful evening ahead.